All right, so this is the lesson for the first, these are the notes for the first lesson in Chapter 2. There's 3 sections of Chapter 2 in the textbook, but we only cover the first 2 sections. So we don't go into a lot of detail about radical functions, and that's mainly because they're fairly simple. A radical function is any function that is based around a root of some sort. The input is being is inside a radical. Now, a square root is the most common radical, but so are cube roots and fourth roots and anything. But we'll primarily work with square roots. And you've been dealing with radicals since grade 10 especially, but we haven't focused on what the graphs of them are like and how they behave and whatnot. And generally, the rest of this course is each chapter kind of focused on a different type of function. And so we'll spend a couple lessons here looking at radical functions. So the simplest radical function, I believe, in my opinion, is just root x. I think a square root is simpler than a cube root. And so what does the graph of root x look like? Well, remember, the square root of a negative number is not a real number. They're imaginary numbers, but they're not real. So we in this course, and we only deal with numbers that are real, not imaginary. And so essentially, the smallest number you can square root is 0, and the square root of 0 is 0. So when x is 0, y is 0. I want to plot some other nice points here. I'm going to pick perfect squares for x. The square root of 4, when x is 4, the output is, I forgot about 1. When x is 1, the output is 1. When x is 4, the output is 2. When x is 9, the output is 3. 16, 4, 25, comma 5. So I've now plotted a good number of points, and so I can visualize how this curve looks. And that's my curve for root x. Notice if you turn your page sideways, or your screen sideways, it looks like a parabola. It looks like the parabola of x squared, but only half of it. And it is actually exactly the same. It's congruent in shape to x squared, except only half of it. And that's because root x is the inverse of x squared. However, x squared is not 1 to 1, and hence the inverse of x squared is, this is only half of it. Anyways, that's the square root of x. And so pretty simple function, actually. The shape of it, again, is related to a quadratic function. The domain of this function is anything greater than 0 or equal to 0. The range is the same. OK, so be familiar with that. So now let's transform this function. And first, I want to just focus on the equations before I actually get into any details of graphs. So for each of these equations, I want to write the equation in terms of x only. And notice the first equation right here is in terms of x and f. So I want to write it in terms of just x and y. I want to describe the transformations in words between this and what f of x looks like. And I want to state the domain and range of each. All right, so first, why don't I'll do the equation first. So remember, f of x is root x in this case. So the equation is 2 times f of x. Well, that becomes 2 times root x. So 2 times root x, all take away 1. The take away 1 is not inside the radical because in function notation, it's not inside the function. There's my equation, right? That's the equation. So what are the transformations? Well, I can see the transformations in either of these equations. That 2 represents a vertical expansion by a scale factor of 2. And this minus 1 out here, which I can also see in the first equation, represents a vertical translation 1 down. All right, and I can see both of those transformations in either equation, either in function notation, which is probably more obvious. If you look in this equation, it directly relates to what we saw in Chapter 1, whereas this is specific to radical equations. That said, what's the domain and range? Well, to know the domain and range, I think it's useful to make a quick little visual of what this must look like, a very simple visual. So for example, here's root x. Okay, the domain and range of that we know are both greater than or equal to 0. Well, let's look at my 2 transformations. The vertical expansion will stretch it and look something like this. I don't care about the details about exactly how high it's being stretched vertically. However, that doesn't change the domain or the range. So far, the domain and range are still greater than or equal to 0. The last transformation is when I move this 1 down. So that starting point is now down here at -1. It looks something like this. And so now if I focus on what I just drew in blue, that's what my quick sort of rough idea of what 2 root x take away 1 looks like. I can now see the domain is still greater than or equal to 0. The range, though, is greater than or equal to -1. And notice that equation that I looked at right here I could visualize really quite quickly like this. I didn't need to deal with any specific points. I just wanted, except aside from the starting point at -1. All right, so let's try the next one. Okay, so here's the equation in function notation again. Again, though, the function f is root x. So I will write this, it's actually pretty easy to write this as an equation. As an equation, it's just the square root of everything I've highlighted in yellow. But in terms of seeing my transformations, that's not so useful. So I do have an equation. What I wrote there, the square root of -1/3 plus 3, is fine. That is the equation. Notice everything that was highlighted in yellow was inside function f, so now it's all inside the square root. But if I want to see the transformations, I can't see them yet. If I look at this, if I want to see all the transformations, the first thing I really want to do is factor out that -1/3 from the x. What I have right here is not wrong, it's not bad, but it's not in the form we're used to looking at in order to see all the transformations quickly. So I want to put it into that form. And so I want to factor out the -1/3 from the x and the 3. So if I take out the factor of -1/3, that means I'm dividing both of these. The x, I'm dividing both of these terms by -1/3. Well, the first part's fairly easy, just x. But now we got to think, what is 3 divided by -1/3? Well, that's the same as 3 times the reciprocal, -3/1, which is -9. Everything I did right here is grade 8 math. So much stuff comes back to grade 8 math. So I know that this other term must be take away 9. So everything you see highlighted in yellow is equivalent. And so I can either write this in function notation or in the actual equation. So every equation you see here is equivalent. I'll erase all this stuff in red down here. In terms of seeing the transformations, I think the last two are definitely the most useful, because now I can see all the transformations. I can see that -1/3, and I can look at either of these equations, but I'll point to this one here. That represents it's inside the function, so that's a horizontal reflection. That's the negative part. Again, if the whole function was negative, it would be a vertical reflection, but the negative is inside the function. As well, the 1/3 represents a horizontal expansion. But the most important part is not the word expansion, it's a scale factor, by a scale factor of 3. As well, though, this -9 here, which I couldn't see before I took out the factor of -9, tells me compared to root x, this is going to move 9 to the right. And again, I can see both those transformations in either of these last two equations. All right, everything I've done, though, right now, aside from this step right here, but really even everything I've done, even including that, is all directly from chapter 1. You don't need to know anything specific to radical functions to write down what I've done. Now, though, I want to visualize the domain and range. So now, again, I want to go back to this basic sketch of first root x. Looks like that. I want to apply these transformations. There's 2 of them. I have the horizontal reflection. I'll do that first. That looks like this. And then it's a horizontal expansion by a scale factor of 3, which means it's been stretched even further out like this. However, that last transformation isn't a big deal. It's the reflection that matters more. So far I can see the domain is less than 0 or equal to 0. The range has not changed. And then 9 to the right. I want to imagine that last thing I drew moved 9 to the right. So it's now over here, going like this. And that's all I need to have a quick visual to figure out the domain and the range. So I can see the domain is everything less than or equal to 9. The range has not changed compared to root x. And that's because all the transformations we have here are horizontal transformations. And so it kind of makes sense. If all you are transforming are horizontal aspects of the graph, that won't affect the range, because range has to do with vertical aspects, outputs. All right, I have 2 more here. Okay, so this time, though, I don't have it written in function notation anymore. I have just the equation in radical form, which in some ways is less work, but maybe it makes it less obvious what the transformations are. But really, there is less things to do here. Doesn't mean it's easier. So first, what are the transformations? Well, I can't yet see all my transformations till I factor out that 4 in front of the x. Because 4x plus 2 is what's going inside the radical. So 4x plus 2 is the input of this radical function. And so if I want to factor out that 4, which means I want to divide 4x and 2 by 4. If I factor out the 4, the first part's pretty nice, but then I get plus 2 divided by 4, which is a half. So that is an equivalent equation that is in many ways more complex than when I gave you at first, but I can see all the transformations. So compared to root x, I have a vertical reflection, because notice the negative is outside the radical. I have a horizontal compression by a scale factor of not 4, but 1/4. And it's being moved 1/2 units compared to root x to the left. All right, those are my transformations. Okay, if that seemed harder than these previous questions, that's because in the previous questions you were probably focusing on the equations and function notation, which makes sense because we've been spending, several lessons looking at that. All of chapter 1 was kind of about that. With that said, though, let's now do the same things as before. Quick sketch. Root x looks like this. I'll look at the transformations, the vertical reflection. I'll do that first. Okay, the horizontal compression looks something like this now. But again, that last transformation doesn't really affect anything in terms of domain and range. And 1/2 unit to the left. So now it's starting, let's say, right here at negative 1/2. Looks something like this. And the domain is now everything greater than or equal to negative 1/2. The range is everything less than or equal to 0. Again, what I'm doing right here, which is connecting back to here, is quite quick. I'm not saying it's easy, but it's quite quick. And again, this is something that computers can't really do so well. Computers can graph these things, but they don't get a quick sense of how things behave. And again, that's always our goal. Our goal is not to recreate what computers do. Our goal is to have a sense, a feeling for things. Computers don't have feelings for things, and that's our goal, to have a sort of feeling for these transformations and these functions. Last one like this. Same idea. I have an equation in radical form. I want to visualize all the transformations in order to understand the domain and range properly. So in this case, I want to do a few things. I want to factor out the 4 from inside my radical, but also I want to rewrite this part here. Dividing the whole thing by 4 is fine, but if I want to make this look as familiar as possible, I'm going to write it as multiplying by 1/4. Dividing by 4, same as multiplying by 1/4. And factor out the 4 from inside the radical. I have this. So these two equations are equivalent, but what I've just written down makes all my transformations compared to root x much more obvious. I'm not saying it is obvious, but it's more obvious than before. So that 1/4 represents a vertical compression by a scale factor of 1/4. Right? I could see that right here, but I think it's more obvious than what I just wrote down in this other equation. This 4 right here is being multiplied inside the radical, inside the function. That is a horizontal compression by a scale factor of also 1/4. And the -1 compared to root x is moving 1 to the left. And now that's what I need compared to root x to figure out my domain and range with confidence. So here I go, back to this. There's root x. I'll make that a bit nicer. Okay, so the vertical compression and the horizontal compression, I could just skip. I know they're going to make no difference to my domain and range. I'll show it quickly. A vertical compression will look something like this. Horizontal compression will look something like, I don't know, like that. I don't really care. In terms of domain and range, all of those transformations don't affect the domain and range. They're not reflecting it. All that will really affect the domain and range is this 1 to the left. And so this graph starts over here at -1 and looks something like this. And so that's all that really matters in terms of the transformations. So if you look at these transformations we wrote down right here and realize in terms of domain and range only this matters, and you just ignore these ones over here, that's fine, as long as you understand what the transformations are. But in the end, my domain is everything greater than or equal to 0, range unchanged. And notice my range is unchanged. I did have a vertical transformation, but I just compressed it. And a radical function goes up forever. So yeah, I compress it, but it still goes up forever. I didn't reflect it. So therefore, the range didn't change. OK, so what I want to do now is focus on the details of these graphs. Use the same sort of ideas, but actually to make a fairly detailed graph for 2 examples. Sorry, I forget what I'm supposed to be doing here. We're not making a graph. I'm giving you a graph. And you want to find the equation. All right, helps if I know what I'm doing here. So therefore, see this time, here is my radical function. What's the equation of it? Well, I will say there's always more than one possibility here. But let's try to, I want to bring this back to root x and think about what's happening to root x to get here. So root x, remember, starts at 0, 0, 1, 1, 2, 4, something like this. Okay, so what can I see here? I can definitely see this has been reflected horizontally. I know this has been reflected horizontally. So I'm going to just write that down right now. I know there is a horizontal reflection. I also know at some point this has been moved down 2 units because of the starting point. You know, a nice aspect of functions like root x or transformations on them is that they have a starting point, and it's hard to, you know, not focus on that starting point at some point. This starting point is still on the y-axis, but it's down 2. So I know at some point there must be a transformation this has been moved down 2. So is that it? Well, let's see. If that is it, let's see what this would look like. If I take that graph of root x and move it down 2 and then reflect it horizontally, it would look something like this. So what I'm drawing in green here, that is the graph of root x if I reflect it horizontally and I move it down 2. And I know, and I was able to, you know, I've just flipped it over horizontally. That's pretty easy, and down 2. And it all comes back to me visualizing this. Now, if we are still struggling to remember the key points on root x, fair enough. What I just drew in green takes a bit longer, but we want to get that down as soon as possible. So what I have in green is just the horizontal reflection and just down 2. It's clearly not enough. So now what's my transformation? Well, one way of looking at it is to visualize it as a vertical stretch, where all these points are going up here. And that's, I say one way because it's not the only way, but it's probably, in this case, the easiest. Okay? And so what is the stretch? Well, compared to where the function starts, right, compared to this sort of baseline right here, all these points in blue are 2 times higher than if there was no stretch. They're all 2 times higher. So that is my vertical stretch. I can see the vertical stretch by a scale factor of 2. And so I now know there's also a vertical, I'll say vertical expansion by a scale factor of 2. And now that I know that, I can write my equation. And so my equation will look like this. The equation of this must be y equals 2 times the square root of negative x minus 2. And again, the 2 is my vertical stretch. Down 2 is going to take away 2 over here outside the equation, and the horizontal reflection is the negative in front. Now there is another way of looking at this, which I will talk about now. Sure, I'll talk about it right now. You could also think about this as a horizontal compression. And so imagine here, I'll get my red marker out nice and skinny. You could also imagine these points in green being compressed this way. Right? If all these points, I could imagine my graph in green, just the horizontal reflection, just a translation, being compressed horizontally into that blue graph, which means there must be some sort of horizontal compression scale factor I could use as well. In this case, I think it's harder, but there must be a way. And I could try to look at the graph, and there is a way I can figure it out from the graph. In fact, if I look at these points here, I can see what the compression must be. Or algebraically, I can do this by remembering some work we did in grade 10 and grade 11 with radicals. That 2 that's highlighted in yellow, I can rewrite that as root 4. 2 is the same as the square root of 4. Okay, so I'm just taking that 2, that vertical expansion, and writing it as a radical. Why am I doing that? Because when I'm multiplying 2 radicals together, I can write them as a single radical. And so I have the square root of 4 times the square root of minus x is the same as the square root of 4 times minus x, or minus 4x minus 2. And if I write it like this, it's no better, but I can see that 4 there must represent a horizontal compression by a scale factor of not 4, but 1/4. And in grade, especially grade 11, you would have spent a fair amount of time in one unit working with radicals, like taking radicals and taking what we call a mixed radical, putting it into an entire radical, and vice versa. So those concepts hopefully sound familiar, but you weren't graphing them. But because you can always take any expression like this, which has a coefficient in the front, if you want, there's always a way. It's not always nice. There's always a way of writing inside the radical and vice versa. That means there's always a way to visualize these transformations, either as a horizontal or a vertical stretch, or both. You have lots of options. Okay. In this case, though, this first example, I think the vertical stretch was the simplest. All right. So same idea here. What is this function? Compared back to root x, I can definitely see right away it's been vertically reflected. And I can see right away it's been moved 1 to the left from that starting point. Okay, so like before though, I want to see, I'm going to assume there's probably some sort of stretch, but to be more than just making a guess, I want to first visualize what just a vertical reflection and 1 to the left would look like, and that would look like what I'm going to draw in red here. So what I'm drawing in red is what the graph of root x would look like if it was moved 1 to the left and reflected vertically and nothing else. Okay, so again, I can look at this in multiple ways. If I want, I can look at this and imagine it being expanded horizontally. Unfortunately, if you look at those points in red compared to these points in blue, I can't actually see any of these points in blue with confidence. I can estimate the y coordinates, but that means my scale factor will be an estimate. Perhaps a good estimate, but I'd rather not estimate. So what else can I do? Well, there must be a way, but let's look at it instead as a horizontal compression and see if there's a way I can do that a little bit easier. So let's look at it going, the points in red going this way. And that last thing I drew is the most useful one. If I look at this point here and how it compresses to this point here, I can see the compression. How do I see the compression? Well, compared to where my function starts, horizontally, if there was no stretch from this starting point, this point here would be 9 units over. Instead, it's only 3 units over. And so 3 is 1/3 of 9. So I can see visually that this graph has been compressed horizontally by a scale factor of 1/3. So a horizontal compression by a scale factor of 1/3. I can see that. It's not easy, but I can see that. So now I can put this all together into an equation. And so as an equation, I would write y equals a vertical reflection, so a negative in the front, inside a scale factor of 1/3. In my equation, I have a 3, right, the reciprocal of it. And then in brackets, if I want to move a function 1 to the left, I want to add 1 to just the x. And that's my equation. That said, what was this scale factor here? Well, I can figure out what that scale factor was if I take this 3 inside the radical out. How do I do that? Well, it's actually pretty quick. I'm going to take that radical and rewrite it as negative root 3 times negative x plus 1. Right? It's kind of the reverse of what I did before. Now 3 is not a perfect square, so if I decimalize it, I get like 1.7 blah, blah, blah forever. I'd rather not do that. But really, I'm done. That's my scale factor. That root 3 is my scale factor. This is also the same as a vertical expansion by a scale factor of, not 3, root 3. And again, the square root of 3 is approximately 1.73. So, but that's it. Oh, I can't write today. Apparently I'm tired. There we go. So that scale factor that I couldn't visualize immediately, that I was looking at first, that vertical scale factor, is actually root 3. Well, it makes sense that I didn't figure it out visually because root 3 is not a rational number. And so, but that's what it is. That vertical stretch is a scale factor of about 1.73. The horizontal compression, which is equivalent in this case, is a scale factor of 1/3. I think that's a bit simpler. All right, there are algebraic ways of approaching this as well, but I'm going to leave that for now. And the final problem I'm going to leave as well. It's not hugely important. I'm hoping we can talk about it in class. I think this video's gone on long enough. All right, so goodbye.